Hi, it's a whole new theme and we're going to focus on the atom. In particular, topic E1 is structure of the atom. And we have two sections to this. We have the standard level section, which I'll be honest with you, is really very easy. Yes! And then we've got an extra higher level section, which takes it a little bit further and maybe uses some language that you're unfamiliar with, but it's not hard, I promise. We're going to go from the very beginning, from the scattering experiment. And this was undertaken in 1911 by Ernest Rutherford. And there was a couple of others there too. Marsden, he was there, a few other people, but he generally takes the credit for it. And what he did in 1911 was he carried out a particle scattering experiment. And we can see the equipment here in this slide. We have an alpha particle source. So in this chamber here, we have alpha particles, and they are directed out of a lead chamber in a very straight line. That means that alpha particles should not be found at any stage behind this lead chamber. Those alpha particles, which are 2 protons and 2 neutrons, so they have a heavy plus a positive charge, are directed towards a very thin gold foil. And when I say very thin, I mean very thin. It's only a few atoms thick. And on the other side of the gold foil, we have a zinc sulfide screen and a microscope. Inside of the whole system is a vacuum. So the idea is that these alpha particles will be directed at the thin gold foil. They'll interact in a certain way with the atoms within the gold foil, the gold atoms, and they'll be detected at the other side by the microscope and the screen. The fact that it's carried out within a vacuum means that these alpha particles should only interact with the thin gold foil and nothing else. Expectations of the atom at that time was that it was a plum pudding model. They expected that protons were like a sort of jelly that pervaded the atom, and electrons were dotted around like plums in a plum pudding. If that had been the case, they felt that these alpha particles would mainly pass straight through this very thin gold foil. And what we have here, these blue spheres, are representations of the atom they felt at that time, the plum pudding model atoms. And these alpha particles, they felt, would never really gain enough repulsion, enough force, electrostatic force, to move them a little bit more than a quick deflection off of their straight path. So they expected most of the alpha particles to travel straight through with very minimal deflection. And that deflection was due to the charge being spread around the atom. What actually happened was very different. And actually, Rutherford described this moment as extremely surprising. And he says it was as though you fired a cannon at a piece of tissue paper and the cannonball returned to hit you in the face. He was very, very surprised by the results, because what happened was the alpha particles largely travelled straight through with a very minimal deflection, but every now and again, very rarely, one would completely recoil. And that recoiling was extremely unexpected, because if we go back to the plum pudding model of the atom, the plum pudding model has the charge distributed over a whole sphere, which means the charge at any point is never going to be strong enough to completely rebound the concentrated charge of the alpha particle. So the very thought that this atom would have enough electrostatic force to completely repel an alpha particle was impossible. This result here, where the alpha particle was completely rebound, totally changed everything. Let me tell you what Rutherford's observations were. Rutherford observed that about 99% of the alpha particles went straight through the gold foil without being deflected. So 99% of them went in a straight line like that. His second observation was that some of the alpha particles are deflected through small angles. Let's go back to our diagram. Some of the alpha particles were very slightly deflected, as you can see here. And his third observation was that around 1 in 8,000 alpha particles were deflected at an angle greater than 90 degrees. So 1 in 8,000 would be deflected at an angle past here, so it would be rebounded from its original direction. From these three observations, he made three conclusions regarding each observation. For the first observation, he said about 99% of alpha particles went straight through the gold foil without being deflected. His conclusion was that the atoms are mostly made up of empty space, as most of the particles pass through without deflection. The second observation was that some alpha particles are deflected through small angles. So his conclusion about the atom based on that was the nucleus of the atom is positive, given that the positive alpha particles were deflected by repulsion. So already we're building up a picture of what this atom looks like. We know that it's mostly empty space and that the nucleus, the centre of the atom, is positive. His final observation was around 1 in 8,000 alpha particles were deflected at an angle greater than 90 degrees. And his final conclusion was that most of the atom is concentrated into a very small nucleus. If the force is large enough to cause the alpha particle to rebound, then that must be the case. So he feels that the positive charge is concentrated into a very small nucleus. So head to your revision note template and go to the other notes section. At this point, I'd write 2 columns in a table with 3 rows. Column 1 would be Rutherford's observations, column 2 would be Rutherford's conclusions, and the 3 rows would be the 3 observations and the 3 conclusions that he drew. You'd want to memorise these for the exams. Next, go to the common diagram section of your revision note template and draw the paths of the alpha particles that were observed in Rutherford's scattering experiment. Finally, complete question 1 in knowledge questions. We talk a lot about the atom and we talk about the nucleus. We talk about the nucleus in terms of radioactive decay, nuclear fission, electron diffraction and photons and all sorts. And the atom is key to that. There are a couple of things that are specific to physics that we want you to know about the atom. And in particular, we want you to be able to describe the structure of the atom and the approximate size of the atom. Here we have a diagrammatic representation of the atom. It's not exactly right, because as you're going to learn in a little while, is electrons sit within energy levels. And this diagram doesn't really show that particularly well. But this is a sort of a standard way that we would represent the atom. And you can see that in the centre of the atom we've got nucleons. And nucleons are particles inside the nucleus. Come on folks, you know what's inside the nucleus, don't you? We've got protons and we've got neutrons. So anything that can be found inside the nucleus is called a nucleon. And the nucleons are found inside this nucleus. And then we've got electrons flying around outside. This atom is extremely small. I hear you say, that's not news, Sally. But did you know they have a radius of 1 × 10⁻⁻10 meters? That's tiny. And what we say is their magnitude is 10⁻⁻10. It's got a magnitude, the size of the atom has a magnitude of 10⁻⁻10 meters. So whilst the diameter of this atom is 2 × 10⁻⁻10, we say that the size of the atom is a magnitude of 10 to the minus 10. What becomes interesting is that actually this nucleus is much smaller. This nucleus is 1 times 10 to the minus 14 meters. It's 1/10,000th of the radius of an atom. That means if you had a whole football field and put a tiny pea in the centre, that would be the nucleus. And the rest of the atom would go outside of the football field. It'd be massive. So don't underestimate how small that nucleus is, because the atoms are never drawn to scale. It's too difficult. You can't put an atom drawn to scale in a textbook. The final thing we know about the structure of the atom is that most of the mass is contained within the nucleus. So the electrons don't have very much mass at all. And in fact, inside the nucleus, we have protons and neutrons, and they have most of the mass. We come to our revision notes. I want you to describe the structure and approximate size of the atom. I think we'll draw a nucleus like this. And let's just, if you don't mind, let's just draw our electrons like this, and you'll see why in a minute, okay? And we'll put 2 electrons on there. Maybe if you're dead clever, you'll know why. So you draw all this, you write down size of atom is 10 to the minus 10 meters. Size of nucleus is 10 to the minus 14 meters. And we'll put most of mass in nucleus. Happy with that? Let's move on. If we have a sense of what an atom is, let me just be brutally honest with you. Physicists are extremely lazy. We do not want to be writing, number of protons equals 19, number of electrons. Oh, boring. Okay, we want to simplify everything as much as possible. So what we do is we come up with notation to explain what things are made of. We want a really quick way to give as much information as possible. That's why we do things like graphs. It explains so much. And in this case, we come up with notation to tell you how many protons are in an atom, how many neutrons, and what the atom is called. So we represent atoms using something familiar to you, hopefully, that looks like this. On the bottom left-hand corner, we have something called the atomic number. And you might remember that instead as the proton number. But this atomic number basically tells you the number of protons that the element has. And it can get a bit complicated when you look at the periodic table, because they're not always set out the way that physicists like to set them out. But in this case here, you can see we've got platinum, and this number here is our atomic number. That's the number of protons. So if we wanted to write platinum in the way that physicists do, we'd write the element symbol here instead of X. Then we'd write the number of protons in the bottom left. And the top left is our mass number, and the mass number is the number of protons and the number of neutrons that are added together. It's sometimes called the mass number, it's sometimes called the nucleon number, because earlier on I did say to you that a nucleon is a proton or a neutron because it's found inside the nucleus. So in this case, it would be 195. If we wanted to find out how many neutrons were in platinum, what we could do is take the mass number, 195, subtract the proton number, 78, and that will give us the number of neutrons. So the number of neutrons is 117 neutrons. It's good for you to, first of all, start recognizing this notation here, but also start working out being comfortable with putting your proton number, your mass number and the element symbol as shown. So we go to our revision notes, and we want to write in our revision notes how to distinguish between the atomic number and mass number of an atom. So we will do this in our other notes. We'll write that down as our atomic number, or the proton number. And up here we'll write this as our mass number, or we can put protons plus neutrons. And here we'll do the element symbol. And if you wanted, you could give a little example here. Okay, so you could give like carbon 12, like that. Let's talk you through spectra, all you need to know. And the learning objectives that you need to be covered are: understand that the absorption and emission spectra for each element is unique. Explain how spectral lines are evidence for the existence of discrete energy levels. Describe how emission and absorption spectra are produced. Calculate the frequency or wavelength of released or absorbed photons using the difference in energy between the energy levels in an atom. I'm going to cover all these in the next 5 minutes. So on with the show. So Rutherford said there's a nucleus, there's electrons flying around it. And that's as far as he got. But if we think about a negatively charged electron and a positively charged neutron, those electrons are going to orbit round, but they're also going to be attracted, because opposites attract. A negative is attracted to a positive. So it's not going to just sort of stay in orbit no matter what forces are on it, because it's going to be attracted towards the positively charged neutron. So what we expect under Rutherford's atom is we expect the negatively charged electron to accelerate into, in a spiral, into the positive nucleus. And in which case, by doing so, that charge is accelerating because it's changing direction. So it's accelerating. Therefore, if this electron continuously changes direction towards the centre of the nucleus, it should give out a continuous amount of electromagnetic radiation. And it wasn't doing that. So Rutherford's model needed revisited. And this is where Bohr came up, Niels Bohr. And he said, well, okay, we know that the centre of the atom, the nucleus, is positive and has neutrons and protons in it. And we know that the electrons orbit around the nucleus. But he suggested that electrons exist in specific states called energy levels. And I like to think of them like stairs. You know, they stay on that one stair and it surrounds the nucleus. And these energy levels have discrete energy. So they have distinct energy values associated with these energy levels. And the electrons can stay in that energy level without radiating any energy. So it doesn't give any energy away. It can go round and round and round, and it stays where it is. And that electron stays and keeps that amount of energy until it transfers from one energy level to the next. It's either up or down. And you can see in this diagram here, we have n equals 1, n equals 2, n equals 3. And what those circles represent are each of the energy levels. And the electrons can stay inside those energy levels, or they can jump up or down depending on how much energy they get. Let's continue on this theme. And Bohr said that these electrons could gain or lose energy only when it made a transition from one state to another. So if we look on the diagram over here, the top electron is in energy state n equals 1, and it wants to move to any energy state n equals 2. So it gains energy to move between those two levels, or those two states. The amount of energy it gains is the amount of energy that's between those two energy levels. And the other electron, you can see it's going from n equals 3 down to n equals 1. That electron will lose energy And the amount of energy it loses is the difference in energy between those two energy states. The electron, whilst it's in the state, whilst it's in n equals 3, doesn't radiate or absorb energy. That only happens when it moves between states. So how does this relate to spectra? So if we have a look at an emission spectra, an emission spectra means you're giving out light, which means that the electrons are giving out energy. Okay, so if we take the example of the down here, we have an atom. There's an electron within the n equals 4 energy level. It gives out a certain amount of energy to go down to n equals 2. That energy that it gives out is a packet of energy called a photon. And we know that a photon is a packet of light. It's a unit of light. So whenever an electron goes between energy states or goes down energy states, it gives out a packet of energy that relates to a photon. And in emission spectra, what you have is you have a black background where there's no photons of light, and wherever these electrons are going between energy states, it gives out a line, a spectral line that relates to that transition between energy states. We're going to talk about that in a bit more, but an emission spectra is when a photon is released that relates to the energy difference between two energy states. An absorption spectra is the other way around. That's when an electron wants to go up an energy level, so it needs to take in energy. So in this example here, we've got the electron is in n equals 2. It wants to go up to n equals 3, so it needs some energy from that. So it takes in a photon of light and uses that energy to jump up the energy state. And when it happens in this way, it's called an absorption spectrum because it removes the photon that relates to that energy transition. So you'll see from the absorption spectrum, we've got a continuous spectrum of light behind it. And then there are black lines. Those black lines relate to what's been taken out, the photon or the photon of light that's been taken out to allow that electron to jump up the state. So how do we then associate the difference in energy levels with the resulting frequency of light that is released? The energy of each emitted or absorbed photon is defined by the electron's transition between energy levels. Using Planck's relationship, it is possible to calculate the frequency of the emitted or absorbed photon. So can you see Planck's relationship down there? Other way. Planck's relationship down there. You've got energy, or the difference in energy, and that is the difference in energy between these states. It's a number. So the difference in energy is equal to h, which is a constant, times the frequency of light. So if you have a number of energy, and we'll work out that in a second, you can work out the frequency of light, or the specific frequency of the photon that is released. And we've got an example here. Instead of showing the energy levels as the round circles, we tend to sort of simplify it to what looks like a series of horizontal lines. And the distance between the horizontal lines are indicative of how much energy is between those energy levels. You can see on this, this diagram here, and I think this is a hydrogen atom, we've got n equals 1, and if the electron is in the n equals 1 state, that electron has 13.6 electron volts of energy. If the electron is in n equals 2 state, that electron has 3.4 electron volts of energy. If the electron is in n equals 3 state, that electron has 1.51 electron volts of energy. This question says, an electron transitions from n equals 2 to n equals 1. Calculate the frequency of the emitted photon. So we go to n equals 2, The amount of energy it has there is 3.4. It wants to go to n equals 1. The amount of energy it needs there is 13.6. Don't worry about the negatives at the moment. Just put them to one side. So the energy difference is 10.2 electron volts. Now we can't put 10.2 into the Planck relationship because it's not in the right units. We need to put it into joules first. So we convert 10.2 electron volts into joules, and we do that by multiplying it by, what's an electron volt? 1.6 times 10 to the minus 19. So it's 10.2 times 1.6 times 10 to the minus 19. That gives us it in joules. And then we use the Planck relationship, as shown below, to calculate the frequency of the photon emitted. Now that photon has one frequency, and that relates to one colour. Okay? So if we go back now to this emission spectrum, that one frequency of photon that is emitted by those distinct energy transitions relates to one colour. And in which case, that would be either the red or the green or whatever. So you see one very thin line of light because it relates to that one frequency. And once you've got the frequency, you can use V equals F lambda to find out a wavelength. So you can find the frequency or the wavelength just by looking at the energy change of these energy states. Now, what about these spectra being unique? Well, if you look at each atom, and I'm going to go back, each atom or each element, so hydrogen, for example, the energy states look exactly like this and they never change. But for helium, the energy states might have different values there. So the n equals 1 value might be minus 14, and the n equals 2 value might be minus 3.6. So they've got different values of energy within the states. That means when you do the transition between the energy states, the energy change is different. The number of energy is different. And when you plug that into the Planck relationship, that gives you a different frequency. And what that has the effect of is that the emitted line on that spectra is a different place in the spectra. So whereas before, that transition we did before may have a green line, if you use helium and do from between N2 and N1, that energy difference is different, so the frequency is different, and you might come out with a yellow line. And they sit, depending on what element you're looking at, the spectra looks different. But for neon, it always exactly looks like for neon. And for oxygen, it always looks exactly like oxygen. And for nitrogen, it always looks exactly like nitrogen. And for xenon, it always looks exactly like xenon. It never changes for that particular element, but each element has a different spectra. Now, you may have noticed that I'm a big softie, and I really want to handhold you through the whole process of IB physics, telling you exactly what to write and exactly what to do. But I have to start letting you go. I have to start trusting your judgment, because you're coming to the end of IB physics. You're in this last theme, and you have to start trusting your judgment on what's important and what's not. I've taught you the main stuff, so now you need to go to your revision note template, and please use that template because it is important, and write your own notes on the energy levels in a Bohr atom and how they contribute to the absorption and emission spectra. If it were me, I'd include a diagram, the formula, and perhaps a sample calculation, just so I can remind myself what it's all about. Then complete questions 3 to 6 in your knowledge questions. For the last few slides, we've been looking at the electrons within an atom and how when they transition, they contribute to spectra. And spectra can tell us so many things about stars and gases and so on. As we move towards the higher level content, I'd like us to look and focus on the nucleus. I'd like us to focus about that central concentrated part at the centre of the atom, and what can we find out about the nucleus? Well, with some basic physics we can find out how big the nucleus is, and there's a new formula you need to learn to determine the radius of a nucleus. Let's go. I'd like to look at this idea of protons coming quite close to each other. So I want to find out more about the size of the nucleus and stuff like that. So if we're going to find out the size of a nucleus, we need to find out the radius of the nucleus. And what you can do is you can use a version of Rutherford's scattering experiment to determine the radius of a nucleus. And here's what you do. You take an alpha particle, this one here, and you fire it really fast towards a nucleus. You give this alpha particle a lot of kinetic energy. Now, this alpha particle is positive. The gold nucleus is positive. So at some stage, the alpha particle is going to stop because of the force of repulsion, and it's going to fire back again. But at that point where it stopped, all the kinetic energy has turned into electrostatic energy. And you can imagine that if you make this nucleus, or this alpha particle, if you make this alpha particle go faster, you may be able to make this distance smaller and smaller until you almost reached what you think would be the edge of the nucleus. And the distance of closest approach represents the radius of the nucleus, because eventually you could make this alpha particle so fast that it effectively hits the radius of the nucleus, and at that point your kinetic energy is equal to electrostatic energy. So if you know the kinetic energy of the alpha particle, you can use the formula in your data booklet for the electrostatic energy. You know what the Q of the gold nucleus is. You know what the charge of the alpha particle is. This is all a constant, so you can use that to work out the radius of a nucleus. Simple, huh? And scientists used this very simple concept of energy considerations and getting the distance of closest approach to analyse every nucleus for every element in the periodic table. And what they found was a very clear relationship to determine or calculate what the radius of a nucleus would be. Their relationship is that the radius of a nucleus, and you can see it on the screen below, R, is equal to R0 A to the power of a third. Okay, what's R0? Well, R0 is the Fermi radius, and that's given in your data booklet. It's a constant number. It's 1.2 times 10 to the minus 15 metres. So that's pretty easy to pop into your formula. A is the mass number, or the number of nucleons in each atom. You've seen that before in the standard level section of this tutorial. So you pop in A and put that to a power of a third, and there you go. You can calculate the radius of any nucleus in the periodic table, or any nucleus in any element or isotope, using this formula. After making efforts to find the radius of every nucleus, scientists then wanted to try and look at the density of the nucleus. And actually, to find the density, we use a very, very simple equation you've seen many times before. We use the equation density equals mass over volume. In the next few slides, we'll look at how we measure the mass and how we measure the density of the nucleus. And we make a very surprising discovery that the density of almost every nucleus in almost any element, any isotope, is exactly the same. Let's go and find out more about this. To find the mass of a nucleus, we use something called a Bainbridge mass spectrometer. And this builds upon some of the things we talked about in magnetic fields. In this diagram here, we have a magnetic field going into the page. It's a uniform magnetic field. And we fire a nucleus into that magnetic field at a 90-degree angle. The result is that it forms a circle, because the force that results from this magnetic field is perpendicular to its velocity and forms circular motion. So we can use this circular motion to find out the mass of the nucleus, because what we've done is we've equated the centripetal force to the force that the magnetic field provides. So mv squared over r equals bqv sine theta. Sine theta is equal to 1 because theta is 90, comes in at right angles. So we can get rid of sine theta. We know the speed of the nucleus, we know the charge on the nucleus. We can find out the size of the magnetic field. We can measure the radius by simply measuring that distance there. And we can determine the speed of the nucleus going into the spectrometer. All those things will tell us what the mass of that nucleus is. So we already know the nucleus radius, we know the nuclear mass. From there, we can find the nuclear density. Because if we say that the nucleus is spherical, Then the volume of the nucleus can be found by using 4/3 pi r cubed. That's the volume of a sphere. We can pop in the nuclear radius that we've just found to find the volume of the nucleus. And finally, the density of the nucleus has been found by mass over volume. And guess what? Scientists have done this. They've found the density of every nucleus available pretty much. And they've found that the density of nuclear matter is pretty much constant in every element. I've just made the statement that the density of all nuclei is constant. How can I make that statement? Well, let's have a look at some basic maths. We assume that the nucleus is a sphere, and we know that the radius of a sphere is given by r equals r₀A to the power a third. So if we put that into here, we get volume equals 4/3 pi r₀A to the third cubed, which gives us 4/3 pi r₀ cubed A, which tells us, because this is all a constant, that tells us that volume is proportional to A, which is the nucleon number. Fine. That means that V is equal to K1A, and K1 is just a constant. But we also know that the mass of a nucleus is proportional to A, because the more nucleons there are, the bigger the mass. That makes sense. So M equals K2A. Now, if we go to density equals mass over volume, we do K2A over K1A, which is the two expressions we found for mass and volume. These A's cancel, and what we're left with is a constant number. So the density of a nucleus is a constant number, and that's why we can say that the nuclei are constant no matter what the number of nucleons inside that nucleus. In this first part of the higher level section of E1, we've looked at how to find the radius of a nucleus using the distance of closest approach, and that would be the experimental way to find the radius of a nucleus. But we've also discovered that scientists did this experiment loads and came up with a formula for the radius. So you need to know that formula. You also need to understand the distance of closest approach and how you equate the kinetic energy of the alpha particle or whatever's being thrown at the nucleus to the electrostatic energy of the nucleus. You'll also want to include notes on how we calculate the nuclear density and that fact that the nuclear density is constant for all elements. And finally, to really cement your knowledge, go to questions 7 to 9 in knowledge questions, and you can download that below. Back at the very beginning of this tutorial, we looked at Rutherford's scattering experiment, and that's where alpha particles were fired at gold atoms and the results were observed. As physics developed, we were able to start putting those alpha particles out much faster, okay? Really high energy alpha particles. And it's noticed that there's different results to Rutherford's experiment when we use high energy alpha particles. The next section of this tutorial will be looking at how Rutherford's experiment changes when high energy alpha particles are used. Let's start by looking at the limitations of the previous Rutherford scattering experiment that we talked about earlier in the tutorial. The original Rutherford's scattering experiment only considered the electrostatic force and didn't use high energy alpha particles. And what they found were the results shown in this section here. They found that most of the alpha particles went straight through. Some alpha particles had minor distortion on their path, and one in around about, I think it's about 6,000, were completely bounced back. And it's this section highlighted in red, that I really want to look at further. If we have very high energy alpha particles, they can get closer to the nucleus than those original alpha particles did. So if you imagine the nucleus up here, and we've got the electron cloud as it was shown, an original alpha particle would have gone like this, bounced off and bounced back. Easy enough, right? But a high energy one is going to get much closer to the nucleus before it bounces back. And what happens when it gets much closer to the nucleus? That is the key here. If alpha particles have higher kinetic energy, so they've got a greater kinetic energy, their distance of closest approach to the nucleus decreases. Why is that? Well, EK is equal to the electrostatic energy, QQ over 4 pi epsilon naught d. If that gets bigger, then this has to become smaller to make everything work because these are all constants. Okay? So by increasing the kinetic energy, we actually get those alpha particles closer to the nucleus. Now, as they get closer to the nucleus, they enter a region where the strong nuclear force becomes significant. And I don't think you've heard about the strong force before. It is an attractive force, and it's much stronger than the electrostatic force. So it's attractive and much stronger. Let's think about that in a little bit more detail. We have the nucleus, and it is positively charged. We have our alpha particle heading towards it, and it's rebounded because it's also positively charged. These forces repel each other. If we get closer to the nucleus, so we've got our nucleus down here, it's positively charged, and our alpha particle, even though it's still positively charged, gets closer and closer and closer to it, it's positively charged still, it enters a region where the strong force acts, and the strong force acts very close to that nucleus. And that strong force is very strong, but it's also attractive. So it causes these alpha particles to attract towards the nucleus, even though they're electrostatically opposed. And what happened was we saw the results in the scattering angles and distributions deviated from those predicted by purely electrostatic interactions. And when they saw these altered scatter patterns, when they whacked these high energy alpha particles at the nucleus, and they saw that actually they weren't being rebounded anymore, they were being attracted into that strong force, it really made them think about how is the nucleus made up. And they realised that it had a more complex structure than just a simple positive charge distribution. They realised there was another fundamental force, and we call that the strong force. So the strong force was identified because they started throwing higher energy alpha particles at the nucleus. It was at this stage that they started to realise that Bohr and Rutherford were wrong, and they needed to start to develop those theories even further to allow us to understand the nuclear structure. It was this realisation that made Niels Bohr go back to his model of the atom and look at it in a deeper way. He'd already described that there were discrete energy levels, but he needed to understand it even further. So in the last part of this tutorial, we'll look at how Niels Bohr developed his model of the atom to include quantization of angular momentum. And in particular, we're going to look at the hydrogen atom. So the next few slides will be us looking at Niels Bohr's understanding of the hydrogen atom. This is not quite a hydrogen atom here because we have too many protons and neutrons in the nucleus, but imagine this is a hydrogen atom. What we have are electrons. These are our green little balls, and they are in their energy levels. Let's just take this electron here. That electron is whizzing round in a circle around the nucleus, and it has speed v. It's also a distance r from the centre of the nucleus. Given that that electron is in circular motion, it has angular momentum. And the equation for angular momentum is mvr, which is the mass of the electron times the velocity of the electron times the radius of the electron. So this electron has angular momentum. And by being in distinct energy levels, Niels Bohr very quickly discovered that not all orbits were possible for the electron. Only those for which the angular momentum is an integer. And by an integer, I mean a number. So let's look at this side of the equation here. N is the number of the energy level. N is equal to 1, 2, 3, and so on. H is Planck's constant. That's a number. You'll find that in your data booklet. And of course 2 pi is a number as well. That's a number. So it was only possible for the electron's angular momentum to have certain numbers based on this integer n. And that led Niels Bohr to conclude that angular momentum for the electron was quantized. What does quantized mean? It means packets. It means fixed values. And that led to Niels Bohr considering specific fixed orbits. Of course, once we have specific fixed orbits, that means that when they move between these orbits, like this, or like this, or like this, they lose packets of energy, or they gain packets of energy. And that allowed us to describe the spectra, which we talked about before. So this was a really exciting discovery that Niels Bohr made when he said that angular momentum was quantized inside an atom, because it allowed us to say, okay, I think we do have specific fixed orbits. And the spectra was experimental proof of that. But it allowed him to take one step further. In this slide, we have a slightly different way of showing energy levels. You're quite comfortable with the nucleus being like this and the electrons being in orbital energy levels surrounding it. What I want to do is just take one section like that and look at that point there. And that's what this is here, okay? So we've got our n equals 1 here, n equals 2, n equals 3, n equals 4, and n equals infinity means that the electron is no longer in the orbit. Electron is free. And using the concept of quantized angular momentum and the idea that these electrons were in energy levels, Bohr was able to derive an expression for how much energy an electron has when it's in that energy level. This is for the hydrogen atom only, okay? Let's just try and apply that to make it clear to you. If you wanted to find the energy of an electron here, in n equals 1, you'd write E equals minus 13.6 electron volts divided by 1 squared. And you'd see that the electron had minus 13.6 electron volts in that energy level. If we go up here, we'd say E equals minus 13.6 divided by 4, because that's 2 squared electron volts. And that gives us a value of minus 3.4 electron volts. So if an electron is in that energy level, that's how much energy it's got. And so on. We can do the third one. E is equal to minus 13.6 electron volts divided by 3 squared, which is 9, and that gives us minus 1.51 electron volts. Bohr was able to allow us to calculate exactly how much energy each electron has in these energy levels. Let me point out a few things about this equation to help you understand it better. This negative sign indicates that the electron is bound to the nucleus. So the lower the energy, or the more negative the energy is, the more tightly the electron is bound. So down here, we've got a very tightly bound electron. And let's go up to the top right here. And if you imagine the electrons in their orbits like this electron here in n equals 1 is more tightly bound because that's positive, that's negative, and they're more tightly bound than they would be if the electron was way out here. So that kind of makes sense, right? The energy is 0 when the electron is free from the atom. So the energy is 0 up here when the electron is free. It's not bound to the atom at all. Another reason why we have a negative energy. Down here, n is only whole numbers. N can be 1, 2, 3, and so on. It's the number of orbit. That means, as we saw before, that the electron can only have certain discrete energy values. And finally, and this is something that a lot of students don't pick up on, is as the energy levels increases in numbers, so we go from n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, you'll notice that those energy levels get closer together. And that's because we've got this n squared value. So as the electron gets further away from the nucleus, the energy levels get closer together because we've got an n squared value. Here's a picture of Niels Bohr. Good on him, right? Because what he did was he predicted a model and he iterated it after learning about other people's understanding of science. And it was revolutionary. It was revolutionary because he introduced the concept of quantization into atomic physics, and that was the key step in the development of quantum mechanics. While the Bohr model that he developed is not entirely accurate, because it was later superseded by the quantum mechanical model, it does provide us with an accurate model of the hydrogen spectral series, and it was a significant advancement for us in our understanding of the atomic structure. Good old Neil Bohr, we're very proud of you. And to round off this tutorial, let's go back to our revision note template, and I'd like you to make some notes on what we've just discussed. We've obviously talked about the scattering experiment and how Rutherford's scattering experiment changed when we started to use high energy alpha particles. Obviously, those high energy alpha particles highlighted the existence of the strong Bohrs. So I want you to go and write some notes on that. I'd also like you to write down Bohr's equations that we've just talked about for his updated model of the atom. Those two equations are the equation for the quantized angular momentum for a hydrogen atom and the equation for the energy levels of the hydrogen atom. Pop them down. Then I'd like you to go to your knowledge questions and complete question 10.